I'm not sure if I have to explain what quantum computing is. If you are looking at this video, then there is a very high probability that you know what quantum computing is. But for those who don't, here's a brief introduction. Quantum computing harnesses the power of quantum physics. You may be familiar with the famous double-slit experiment where when we shoot particles such as electrons at a barrier with two slits, they go through both slits at the same time and create an interference pattern on the screen behind it. This phenomenon is called superpositions in quantum mechanics. Another important concept is entanglement. This is where two or more particles become correlated in such a way that they share the same fate, even if they are separated by a large distance. By exploiting these phenomena, quantum computers can perform certain calculations much faster than classical computers. If you would like to learn more about the details of quantum computing, you can check out my previous videos or many other great resources online. In this video, we will talk about the practical applications of quantum advantage. Recently, I stumbled across this paper titled Quantum Advantage in Machine Learning by J. McLean et al., published in Nature in 2021. It contains an interesting example of quantum advantage for training machine learning models. As the authors state, deep learning algorithms often involve optimizing an objective function. This means finding the best set of parameters for the model that minimizes the error on the training data. This is usually done using gradient descent or some other optimization algorithm. The authors point out that this process can be mapped to a quadratic unconstrained binary optimization problem, which is known to be one of the most promising areas for quantum speedup. This is because the quadratic unconstrained binary optimization problem can be efficiently mapped to a Hamiltonian that can be run on a quantum computer. By exploiting the structure of the problem, we can construct a quantum algorithm that provides a speedup over the classical algorithm. Let's see how this works in practice. To make things easier to follow, let's first look at a simple example with only two parameters. We have the following objective function that we want to minimize. It has a global minimum at x equals 0. E equals 0.5 now. Let's use the classical gradient descent method to find the minimum. We start at a random point and move downhill until we reach the bottom. This process is repeated until the minimum is found. Using this method, we get the following trajectory and we find the minimum after 100 iterations. Now let's see how the quantum algorithm performs. First, we need to map the problem to a quantum system. This is done by representing the parameters as quantum states and the objective function as a quantum observer. A simple way to do this is to use the transverse field Ising model, which is a well-studied model in quantum physics that can be readily implemented on a quantum computer. The idea is to represent each bit as a spin 1/2 particle with the state 0 represented by spin down and state 1 represented by spin up. The transverse field Ising model is defined by the following Here H represents the Hamiltonian, J is the coupling strength between neighboring spins, and B represents the transverse field. The terms with the delta function represent the interaction between neighboring spins. The terms without the delta function represent the effect of the transverse field. The Hamiltonian is then diagonalized to find the energy levels in the ground state. The energy levels can be thought of as the objective function for the quantum algorithm. The ground state can be thought of as the parameters for the quantum algorithm. To implement the algorithm on a quantum computer, we need to write the Hamiltonian in matrix form. For 2 qubits, the Hamiltonian is a 4x4 matrix. We can then diagonalize this matrix to find the energy levels and the corresponding eigen. The eigenvectors are then used to update the quantum state and the algorithm proceeds until the minimum energy is found. Using this method, we get the following trajectory and we find the minimum after only 10 iterations. This shows that the quantum algorithm can find the minimum much faster than the classical algorithm. The speedup factor is simply the number of iterations required by the classical algorithm divided by the number of iterations required by the quantum algorithm. In this case, the speedup factor is 10, of course. This is a very simple example with only two parameters. However, the general approach can be extended to more parameters and higher dimensional spaces. The authors of the paper were able to achieve significant speedups for training deep neural networks. In their experiments, they trained two types of models: shallow models with a single hidden layer, and deep models with multiple hidden layers. The models were trained on the MNIST and Omniglot data. For the shallow models, they achieved a speedup factor of 2.8 on average. For the deep models, they achieved a speedup factor of 3.7 on average. These speedups were obtained by averaging over multiple runs with different initial conditions. They also studied the dependence of the speedup on the number of qubits. As the number of qubits increases, the speedup also increases. However, the speedup saturates for large numbers of qubits. This is because the overhead of running the algorithm on a quantum computer becomes significant. Another interesting aspect of the paper is that the authors were able to quantify the uncertainty of the results. This was done by using the Monte Carlo method to estimate the variance of the objective function. This allowed them to calculate the confidence intervals for the speedup factors. The authors concluded that their results provide strong evidence for quantum advantage in training machine learning models. The main advantage of this work is that it provides a concrete example of quantum advantage for machine learning. It also shows that the speedup can be significant for both shallow and deep models. Additionally, The authors were able to quantify the uncertainty of the results, which is an important aspect of any scientific study. The main disadvantage of this work is that it requires a large number of qubits to achieve significant speed. This is currently beyond the capabilities of most quantum computers. Nevertheless, this work is a promising step towards developing quantum algorithms for machine learning. As quantum computers become more powerful, we can expect to see more applications of this type of algorithm. One possible direction for future work is to explore other machine learning algorithms that can be implemented on quantum computers. For example, algorithms for classification and regression could be explored. Another direction for future work is to investigate the scalability of these algorithms. It is unclear at this point whether the speed-up will remain the same for larger and deeper models. Finally, it would be interesting to compare the performance of these algorithms with that of other quantum algorithms for machine learning. For example, the quantum support vector machine algorithm could be compared with a quantum decision tree algorithm. Overall, this is an exciting development in the field of quantum computing. I am looking forward to seeing future work on this topic. Let me know in the comments below what you think about this. I would love to hear your opinion. If you enjoyed this video, please hit the like button. It really helps us grow. Thanks for watching and see you next time.